This is Physics 2212, Lab 1, Charged Tapes by me, Adil Abdu.
In this lab, we will be using two pieces of charged tape to answer questions about the relative strength of the charges and how much excess charge is on each piece of tape. To conduct this lab, we will use two pieces of Scotch tape in a real-world experiment, as well as a computational model, GlowScript, to perform the calculations. For a preview of the results, the charge on each tape was found to be 1.1118 times 10 to the negative 3 coulombs. The number of electrons lost on each piece of tape was 1.132 times 10 to the 16th. Below are some of the fundamental physics principles in this lab. The first is Newton's second law. By showing that the change in momentum over the change in time is equal to the net force, it is useful in this lab, as we know that the net force will be equal to 0 because the momentum of the piece of tape is 0, as it's not moving. For the second equation, the electric force, we use this to find the charge on each piece of tape, as we know that electric force is equal to the third equation, the gravitational force, which is equal to the mass of the tape times the acceleration due to gravity. We'll go into the methods of this experiment. The first step is placing down one piece of tape on a table. Then we take another piece of tape of equal length and lay it on top of it. We then rapidly pull it off, and by doing this, we take some of the electrons off it. This leaves one of the pieces of tape positively charged and the other one negatively charged. We repeat this step for one more piece of tape. Then, to see whether each of the pieces of tape are positively or negatively charged, we hold it up to another charged object. In this case, I used a negatively charged pen. When I held this pen up to the pieces of tape, I found that they were attracted to it, meaning that the pieces of tape are positively charged. The next part of the experiment is placing the two pieces of tape close to each other. By doing this, we can see that at some distance between the two pieces, the net force will be equal to 0, meaning that the top piece of tape will not be moving. This happens because the electric force coming from the bottom piece of tape is equal to the downward pull from the acceleration due to gravity. This means the net force is 0, and that the F of g is equal to the F of e. Here are results from the following experiment. For the system and the surroundings, we can define our system in this case to be just the top piece of tape, and our surroundings to be everything else, including the bottom piece of tape and the Earth. This allows us to account for just two forces on our system, the electric force from the bottom piece of tape and the gravitational force. Our initial conditions are also just two pieces of equally charged tape placed a slight distance apart, assuming that there are no other forces acting on it besides the Earth and the bottom piece of tape. The data collected includes the tape length of being 8 inches or 0.2032 meters, the tape weight being 0.0002032 kilograms, and the distance between the pieces being 0.019 meters.
The first part of the computational model is a simple GlowScript code. In this code, we model each of the pieces of tape as a single point charge, making the free body diagram extremely simple. An upward force in the middle and a downward force also in the middle, just like it was drawn in our experiment slide. We then find the force of gravity by multiplying the mass times g and set this equal to the electric force. From there, we solve for the electric force, as shown on the right side. By doing this, we find the force of gravity to be 0.002276, electric force to be equal to that, and the electric charge to be 8.96 times 10 to the negative 9.
Part 2 of our GlowScript model, we now look at the pieces of tape as line charges rather than singular point charges. This led to a different final charge as well as a different force of gravity. We will analyze these discrepancies in the next slide. Assumptions, approximations, and idealizations. Throughout this lab, we made many conclusions that decreased the accuracy of this experiment. This included approximations of the weight of our tape and assumptions that no other forces were acting on the pieces of tape. Both of these were not very accurate. Another big assumption that came from the charges. For this experiment, we assumed that the charges were equally distributed along the tape, but this was most likely not the case, which could have led to false results. What if and why? For the first question, we're asked if the charges were reversed and negative instead of positive, what would change? If the charges were reversed, the net effect on the system would be exactly the same. This is because the two charges, both negative, would still be the same, causing them to still repel. Meaning, for the top piece of tape, it would still just be one electric force going in the upwards direction, and one force of gravity going in the downwards direction. For the second question, we're asked, there's difference for the two computational values of the charge, Q. Why are they different, and which is more accurate? The difference in the two values of Q come from the way the charge is computed. By setting up the second model as a line charge, it is more accurate as it is closer to representing an actual piece of tape. It still is not extremely accurate, as a piece of tape would be closer to a rectangle charge rather than just a line.